Okay, so we're going to do some examples and see how this plays up and see how the essential question is going to get us where we're going. In the world that we live in, a lot of times you guys were using rulers, and we have a few rulers here. Here's one, and here's one to do measurements. So someone says, how far is point A to point B? What is that distance? What is the length of that? And you might use a ruler to do so. We have two examples where we have a ruler, and letter A, our ruler doesn't have a whole lot of information. The best we're going to do here to come up with the distance from A to B, you might want to even count it off. Here's 1, 2, 3, and we almost get to 4 on our ruler. And so maybe we say something like AB is equal to, or let's actually restate that as approximately, because we're really not sure what's going on there. We'll call that approximately 4 centimeters. On B, on the other hand, this ruler is a lot more distinct. We've got some pretty good graduations for what's going on. And if I were to count the little ticks from 3 to where my point ends, I would have about 7 little ticks in there. So that's given me a little more information than the first situation. So here I might say less approximately and more distinctly, the answer would be more like 3, maybe 0.7 centimeters. And in some cases on a number line, we might just count the ticks from one point A, in this case, to point B. In our situation here, we're using a ruler. But in the world of geometry, there will be few rulers used to make decisions on the lengths of items. We're going to use geometric concepts. Let's talk about what I just wrote above. It says, how do we explain the difference between the length of a segment and the name of a segment? AB with a line over it, we just learned, describes line segment AB. If I were to say, hey, that's line segment AB, I would know that because there's a line on top of it. It doesn't have 2 arrows, so I know it's not the actual line. It's actually line segment AB. Here, AB, notice there is no line above him. Okay, he is nothing more than 2 letters sitting next to each other. That describes the length or the distance between, or the length of, line segment AB. And that's important because it will be described that way when we're talking about a pure number, meaning how much is AB. In letter A was approximately 4 centimeters. In letter B it was pretty more distinctly 3.7. Okay. So let's talk about what we like to call in geometry the segment addition postulate. I'm going to just make sure you understand what that means. Here's how it plays. It says, how do we find the total length of a line segment if the parts of the segment are given? So you all have a segment on your page, and we're going to call this segment AC, meaning I've got point A at one point, end point, and C at the other end point. And we're going to put another point on our line segment, and we're going to call that point D. And then someone were to tell me that AD was equal to, let's say, 5, and they said that DC was equal to 7, and the question was, how much is AC? How much is the whole thing worth? So how can we play this? The AD is 5. I'm going to show that here. I'm going to say, all right, from A to D is 5 units. I don't know what the units are. We're just going to leave it as 5. DC, meaning from point D to point C, is worth 7. So I'm going to show that with some brackets. And they want the whole thing. And maybe we show that on one large bracket and we put a little question mark there. So algebraically, this is how this is going to play out. If I go from A to D, and I add the length of D to C, I should get the entire length AC. We call that part plus part equals whole. I'm going to now substitute the information I was given. AD is 5, DC is 7, AC we don't know, so we'll call it an X because we like the X variable. And when I add 7 and 5, I get 12. So my x is 12, or more importantly, my AC is equal to 12. This concept will continue throughout this unit. It's not always going to be this simple though. So let's see how this plays out a little differently. Here it says, how do we find the remaining length of a line segment if part of the line segment is measured and we know the whole length of it? I don't know if that grammar was perfect, but we're going to go with it. So here's a line segment, and let's give this endpoint the name S, and let's give this endpoint the name T, and let's put ourselves a point in between. We call that the in-betweenness of points. That's really what it is. It's kind of ridiculous, but we'll call that a U. So again, we're going to be given some information about the lengths of the pieces as well as maybe the whole piece, and then we've got to determine some information. So if they were to tell us that ST, and that would be the distance from S all the way to T, okay, let me undo that, is equal to, let's say, 15 units of some sort. And then they were to tell me that, let's say, UT is equal to 6, and they want the measure of US. We don't know M, so we're going to call that X. Then our setup is going to look identical to above because this is always going to work. Part, meaning part STU plus part U to T will equal the whole thing every single time, no matter how it's presented. So let's see how this plays over here. Let's write it out. SU plus UT equals the whole thing ST. I'm going to show the pieces on here just to make sure I can kind of see it. From S to T is 15, so I'm going to show that with a little bracket here. From U to T is 6. I'm just going to put a 6 above where UT is, and then I'm going to put an X where SU is, and that can tell me kind of how these pieces and parts play out. I'm going to substitute now. My SU is what I'm looking for, so I put an X plus 6 is my UT is equal to 15. So we need to solve at this point, and we're going to subtract a 6 from both sides. So we've set up our algebraic equation, and our answer should be, what is that, 9? Now, some of you guys might have looked at this and said, yeah, it's 9. You just knew it because you can intuitively see this, okay? But here's the problem. It's not always going to be a pretty number 15 and a pretty number 6. Very likely you're going to see representations with X's for each of those pieces and parts. So the setup here is really important as we progress through the unit. Let's go to the back of the page. If you need to jot any of this down, please do so. Please pause the video and then go to the back of the page. This says, how do we draw a figure to represent xz is equal to xy plus yz? This is identical to what we were just doing, where we said part, which was xy, plus part yz is equal to the whole thing xz. So I just flipped that around with my symmetric property of equality. X to z, here's my x, here's my z, here's a y in between. Let me show that in blue so I can be consistent. Now we have an example where things get a little crazy, okay? Using the concept we just talked about, we're going to draw ourselves our own picture to solve this problem. It says find the value of a, so here's our variable. If y, big Y, is a point between x and z. Then they give us some information about each of those segments. Now let's draw ourselves our original segment. They tell me that y, right here, is between x and z. So I'm going to draw myself a picture so this looks prettier for me. They tell me that xy is 3a, so I'm going to put a 3a here. They tell me that yz, or the whole thing, they tell me, let's see here, is 5a minus 4. And then they tell me yz is 14. Well, at least there's a number there for me. I'm going to use the same concept I've been using, where I do part, which was xy, plus part, which is yz, is equal to the whole thing, which is xz. And now I'm going to substitute, and trust me, we can't just do some subtraction here because we've got some variables in different places. XY is 3a, YZ is 14, and that is equal to the whole thing, which is 5y minus 4. We've got ourselves an algebraic equation. We're looking to solve for a. We're not necessarily looking for the actual piece, meaning the distance from x to y, although once we can get what a is, we could substitute him in to determine what he's worth. Let's do some algebra real quick. We're going to subtract a 3a from both sides. That's going to get us 14 is equal to 2a minus 4. And then we're going to add a 4 to both sides. And we should get 18 is equal to 2a. Divide both sides by 2. And our a is equal to 9. Here, if I were to ask you what the measure of xy is from x to y, they told me it's worth 3a, and I found that that a was worth 9. So I'm going to substitute the 9 here to get that xy is equal to 27, whatever the 27 units might be. So that's the way this concept's going to roll. All right, you guys have a U-try. I want you to pause the video and find the value of x. This time we have our happy variable x. If big Y, the point, is between x and z, and make sure you draw yourself your segment and label those 3 points accordingly, and then put the information that you know about each segment there, and then solve from there. Check your work when you have finished, but again, pause the video and try it out. Okay, and you should have gotten that the answer was 87.5. Yeah, I'm sorry, it's a decimal. But hopefully your setup looks correct, and if it does not, will you please raise your hand so we can make sure you're understanding how to play this. Once you get to some problems on your own, you're going to need to make sure you do. The next question says, what does congruent mean? And we're going to use the term congruent a lot in geometry, and it pretty much means that the measures of at least 2 items or 2 figures are the same. The measures of 2 figures are the same. It could be 2 segments, as you see here. It could be 2 triangles. It can be a lot of different things in geometry. It's another way of explaining equality. And so how do we show that the 2 figures are congruent? So we will use hash marks for our segments anyway. We're going to use some hash marks to show that segments are congruent. We've got a couple of segments here. Let's name this segment XY and this segment BC, meaning we're going to give those points the names. And we're going to show they're congruent. If they were to offer that to us and say that XY is congruent to BC, we would show that with a little hash mark here and a hash mark here. And by just having the hash mark on the picture would be enough for us to know that XY and BC are the same measure. We can also see it like this. Let's draw ourselves our own couple of segments. Here's a segment. We'll call this segment AB. And then here's another segment, and it's segment ST. Whoops. And listen, I don't know for sure that those are the same length, and yours probably are not the same length. But in the world of geometry, if I have a symbol to show me something is the same length, then it is the same length. We're going to go with that concept. And another way we might show AB is congruent to ST in this case would be to have 2 hash marks. There's no real rhyme or reason with the number of hash marks that you put onto your segments to show congruency, but having the situation in front of us, we would then know that XY and AB, for instance, are definitely not congruent, but that XY and BC are definitely congruent because of their hashtags, which shows 1 here and 1 here. So how do we show that with a symbol? Because, you know, we like symbols in mathematics. For my XY and BC, I would show it like this. Segment XY is congruent, this is the symbol for congruency, to BC. And I would also say, based on the 2 hash marks on AB and the 2 hash marks on ST, that segment AB, again, not the length, we're talking just the segment itself, that's why I have my line above the AB, is congruent to segment ST. That's how it's going to be presented to us throughout the semester. So based on what we just did, take a minute and jot down what you think this question asks. It says, what does AB congruent to DC mean? Draw a picture. Why don't you make a little note on your paper and then pause the video and take a look. And so this is maybe what you wrote down. AB is the same measure as DC, and I do need to correct a mistake here. You really should show this with a line over AB and a line over DC in the world of geometry. If we're using the term congruency, we're actually discussing the relationship between the 2 segments, not necessarily the relationship between the lengths or the measures. It's a little awkward and confusing, but you'll get there. All right,